Welcome back to BitLearn. This is a series on modern operating system design. In the previous episodes, we looked at how processes and threads create this illusion of parallelism, where you have multiple applications running at the same time. We looked at CPUs, how we schedule work across competing tasks. We looked at memory management, how each process is given its own address space. We looked at virtual memory, IPC mechanisms, pipes, message passing. So today we arrive at one of the most important topics in operating systems: synchronization. Because the moment programs begin to run concurrently and they start sharing data, a new class of problems appear. They are very subtle, difficult to reproduce, and devastating if it is not dealt with at design time itself. So that is this episode. If you have missed any of the previous episodes, please do go back and check out the episodes on the fundamentals of operating system design. It's a slightly academic topic, but of interest for a lot of people. Do subscribe and leave some comments down there if you like the series. And just make sure that you also check out the description, where I'm also coming up with a book which you can buy and use it as a reference. Not a pure textbook, but more of a descriptive version of how operating system design is handled. So with that, let's jump into today's episode. Today's episode is about concurrency and the problems that comes with concurrency. Concurrency is basically trying to do multiple things at the same time. It's running parallel applications. So if you look at a modern computer today, they are concurrent systems, right? You have multiple processes running, multiple threads, multiple CPUs. So if you take your laptop, you're probably looking at the video right now. There's a browser open, there's a clock, there's a taskbar, so many things going on. So to the user, this feels very natural. Programs, they just simply run. But internally, this creates a set of fundamental challenges that have to be dealt with in design. It's a shared state. So the entire hardware resources is shared by multiple applications, multiple processes. So whenever multiple threads access the same data or data structure, the correctness of the program can depend not on what operations are performed. It's basically about when they occur. What operations are different? So for example, the browser is reading something from a socket from the network. That is a what. But the question is, when is it reading? Is it trying to read at the same time when maybe my music streaming application is also trying to read data? It's about when it happens. So in a sequential program, it's pretty straightforward. One instruction executes, the browser reads data to show something on the page, then the music streamer will go to its music streaming site and get its set of bytes for music. Fine, it's all sequential. But if you look at it in real time, for a user, it appears like everything is going on in parallel, right? Music is streaming, the browser is able to access something on the network. So in a concurrent system, the order of operations may change every time the program runs. So and that brings up a whole set of problems. It's called race conditions. So consider a very simple example. We have a piece of code where there is a shared variable where you have x as a variable. We are going to assign the value 5 to that. So let's have two threads which are executing. They are using the same shared variable or shared memory, where the two threads attempt to increment this value at the same time. One of them does x is equal to x plus 1, so the value becomes 6. And the second thread also goes into the same variable, accesses it and makes it x is equal to x plus 1. It's supposed to be 7, right? But that's not always guaranteed if you don't use synchronization mechanisms. You might expect the result to be 7, but computers do not execute this expression in one step. So let's say the first thread reads the variable x. It sees that okay, it has its current value as 5 and I'm going to add 1 to that. At that moment, that thread is interrupted. It's set aside. Another guy comes in, a different thread, which also reads the same variable. He reads the value, oh okay, it is 6, so I'm going to add 1 to that. By the time it's interrupted, I give the control back to the first thread, which assume that x has a value of 5. I'm going to add 1 and I'm going to make it 6 and store it. The second thread, which had already read the variable's value as 5, it assumes that the value is still 5, it adds 1 to that, writes it back as 6. So two threads ran, both of them incremented. Instead of getting your answer as 7, you got 6. It's a made up example, but it kind of shows you the problems that we run into with concurrent systems. So nothing in either thread was individually wrong. They were working fine. The problem was because of how we interleaved these operations. This leads to a condition called a race condition. A race condition occurs when the outcome of a program depends on the timing of concurrent executions. So race conditions are dangerous because they are often non-deterministic. You can't predict what is going to happen, and the program may run correctly hundreds of times, but at some point it may fail. So it's very hard to debug as well. So that's what race conditions are all about, and that is a direct outcome of having concurrency in a system. And this can be handled very nicely with synchronization. So we'll look at that. We'll look at one of the mechanisms used to protect these kind of race conditions. One of them is called critical sections. So to prevent race conditions, we identify portions of code that access this shared data. These regions are called critical sections. So for example, in our previous example, we had a variable x. So when we say x is equal to x plus 1, what was happening in that instruction was it was accessing the variable x, reads the value. Now it knows that the value is 5, and now it's going to add 1 to that. Whether the thread is interrupted or not interrupted, it assumes that the value x is going to have the value 5, which means for the execution of that instruction, the x or the variable x is supposed to have its value 5 stored deterministically. So that whole section becomes a critical section, saying that there is an assumption we are going to use to execute or complete this set of 2 or 3 instructions. So a critical section is a region of code that must be executed only one thread at a time with respect to a particular resource. So the goal is to ensure that the shared data remains consistent. So a correct solution to the critical section problem must satisfy 3 important properties. One of them is mutual exclusion. So when the operating system or the execution pointer comes to the critical section, the area where you check for the value x, you read the value 5, then you add the value 1 to that and write back 6 into the variable. All of these 3 statements are they should be executed atomically. What I mean by that is this is so critical that no other thread should interrupt the variable's value at this point. So what happens is the other thread is actually kept suspended until the critical section is completed by the first thread. So only one thread can execute the critical section at a time. The second is if no other thread is in the critical section, then the other threads will be able to enter that part. So a thread should not wait forever while others repeatedly enter the critical section. So if you have 3 or 4 threads running, which are all trying to increment the x value, you don't want to suspend the other threads infinitely. So let's look at how do we communicate to the other thread that my job is done. You can enter the critical section now. So that's where locks and mutexes come into picture. The simplest tool used to enforce mutual exclusion is a lock. A lock is think of it like a buzzer. Before you enter a critical section, if you are able to acquire a lock, if you are able to press the buzzer and you sound the alarm saying that I'm entering the critical section, then you are free to go in. You have announced, people have heard you, now you can go into the critical section, start incrementing the variable. So it's like before entering the protected region, a thread must acquire the lock. So if the section is already used up by or in use by another thread, somebody else would have pressed the buzzer, which means the light is on and you can't get into it. So it's like a on-air. If you have seen those recording studios, you have this on-air light, right? If the light is on, then you can't go into the studio. Somebody is doing a recording, they are broadcasting. Once the light is off, that's when you can go in. So the light is more or less the lock that we are looking at. So after finishing the work, the thread releases the lock. If another thread tries to acquire the lock while it is already held, that thread must wait. A very common form of lock is a mutex, short for mutual exclusion. Only one person can lock and go in, do his job, come back and release the lock. The basic pattern is the same. It sounds simple, but implementing this lock requires a lot of support from the hardware itself. Because if 2 threads try to acquire the lock at the same time, the system must ensure that only one of them succeeds. So both these threads, they are trying to increment that variable. Both of them check for the lock. If both of them think that, okay, the light is off, so I can turn it on or I can acquire the lock and go into the critical section, somebody must play the mediator. So that is where atomic instructions come into play. An atomic instruction is something that cannot be separated out or broken further until it is completed. So modern processors provide a special instruction that can execute instructions atomically. Atomic means the operation cannot be interrupted midway by another process. So typically it is a test and set or a compare and swap or fetch and add kind of an operation. These instructions allow the operating systems to implement locks safely even when multiple cores attempt to manipulate the same memory locations simultaneously. So in many ways, atomic operations form the lowest layer of synchronization. Everything else, they are built on top of that. Locks, semaphores, monitors, they're all built on top of the atomic lock. So let's look at a spin lock and a blocking lock. Not all the locks have to behave the same way. So we talked about the on-air red light in a studio, right? So if somebody is inside the critical section, the on-air light would be on, so that that lock has been acquired by the person who's using the studio. So when a thread tries to acquire a lock that is already held, it has two options. The other person, in the example of a studio, waits outside until the person recording finishes and comes out, and then he can go. So this is called waiting actively. I keep on waiting. I keep watching the light. Is it off? No. I can look at it. Is it off? No. Or it can sleep and let the scheduler run another thread. So I am a different, person or a producer. I can walk out, go get my coffee, and come back. So it's like a sleep. I go out for 5 minutes or 5 seconds or 5 milliseconds, and I come back. So this lets the scheduler run another thread while I'm out for coffee. So the whole idea is you're not blocking. You either go to sleep or you release your execution. Of course, you can wait actively, but it will hold up the CPU because the CPU has to be allocated to you to check if the light is on or not, to check if you can acquire the lock or not. So next we have the spin lock. A spin lock, this is useful when locks are held for a very short period, because putting a thread to sleep and waking it up can be more expensive than simply waiting. So what a spin lock does is it will actually increment the lock's value, saying that I'm up, I also acquired the lock, I go ahead and do my job. So spin locks are useful in certain occasions, not everywhere. However, if the lock is held for a longer period, spinning wastes the CPU. So in those cases, the operating system uses a blocking lock. So we talked about spin locks, we talked about blocking locks. So spin locks allow you to still acquire the lock, just up the number, saying that I also have acquired the lock, I will go and do my job. So this might be useful where if I'm trying to do the same kind of operations, so I can actually try to use a spin lock. So kernel designers, they kind of carefully choose between these mechanisms depending on the context. Now let us come to semaphores. So semaphores basically enforce mutual exclusion. Sometimes we need something more flexible. For example, imagine a system with a limited number of buffers. Multiple threads may be using this buffer, but only a fixed number of the buffers exists. So that is where semaphores become useful. A semaphore maintains a counter representing the number of available resources. Two operations control the semaphore. The first is a wait called P. This operation decrements the counter and blocks the thread if the counter becomes negative. The second operation is a signal, sometimes called as V. This increments the counter and wakes a waiting thread if one is existing or one is waiting. So semaphores can represent both simple locks and it can manage a pool of resources. So the next one we look at is condition variables and monitors. So many synchronization problems involve waiting for a condition to become true. For example, a consumer thread might need to wait until data appears in a queue. So simply locking the queue is not enough. The thread must sleep until something changes. So that is a conditional lock. Then we also have monitors, which are constantly monitoring a particular state. Once the state is assigned, it will signal whoever is waiting on the monitor. So these are different synchronization mechanisms that are made available in an operating system. Even with all these things, we run into race conditions. That is when we have a possible failure called a deadlock. A deadlock occurs when threads become permanently blocked waiting for resources. Let us say I am waiting for a lock A, but I'm waiting for two locks, lock A and B. So I take up lock A, I try to go to take lock B, but that is not available. So let's say a second thread is going to take up lock A, but since I hold the lock A, it's going to wait forever. So it's like a deadlock, one waiting on the other to be released. So deadlocks occur when threads become permanently blocked waiting for a resource. So yeah, that basically explains the kind of problems we face as operating system designers. Thread A holds a lock and waits for lock 2, thread B holds lock 2, waits for lock 1. These are all going to lead into deadlock situations, even with all these mechanisms that we have, like monitors, conditional variables, semaphore. Even with all those things, it's up to the developer and programmers to put in some thought into making sure that they're using the right synchronization mechanism. So that is about deadlocks. Then we also have this situation of starvation and priority inversion. So even with deadlocks, synchronization can create even smaller problems. One such issue is starvation, where a thread may repeatedly fail to obtain a lock because other threads are continuously acquiring it. So I'm not even able to get into my studio to do my recording. The light is constantly on. So how do we affect that? So that's where priority comes in. The high priority thread, if it keeps running, a lesser priority thread may be indefinitely delayed. So operating systems address this using techniques like priority inheritance, temporarily raising the priority of a thread which is holding the lock so that it may finish its job and release the lock quickly. Different mechanisms. You can look at all these details. Like I said, if you can check the description, there is a textbook or a small a primer I'm writing about modern operating system design. It is not a complete textbook, but it is a great primer to start reading about all these topics. So do check that. You will find a lot of details in it. So the last topic is basically about how do we start going into file systems and IO using all this synchronization, because synchronization becomes even more critical when we consider using files and IO. So different processes might be holding locks for different files. Multiple processes may be trying to read or write the same file. A lot of possibilities are in there. Buffers, caches, these are another area which are shared across the entire system. And the disk operations, they kind of occur asynchronously. So all of this kind of leads us into the next episode, where we are going to look at how do we apply all these synchronization mechanisms when we are doing file IO. So that is file systems and IO in the next episode. I hope you are able to follow what we are talking about in this one. So I will quickly close this episode here. I hope you're enjoying and hope you're using this to learn more about modern operating system design. So if you like the content, do subscribe, do like, drop some comments so that we can have some discussions around this. And of course, do check the description for a book that is coming up. It kind of consolidates all the different episodes we have talked about so far. So meanwhile, keep learning and do come back for the next episode. Thank you for watching.